So, welcome back. In this particular lecture, I am going to talk about one of the very important industrial problem, how to design control system for the power converters. Obviously, in this lecture, I am just going to talk about DC to DC converter, but one can able to extend this approach for any classes of the converter. And this is the last lecture of this particular course, sliding mode control and the application. So, I am also going to share some kind of moment, okay, which I actually expand and learn this course with several the well established researchers of this field, including the one of the founder, Professor Utkin. So, I am going to discuss also about that. So, purpose of the discussion. So, we are going to talk about the development of sliding mode control for the power converters. And if you see the current era, so in industry, because everything is switching towards the electrical vehicle, so application of these kind of converters are very useful, okay, for charging design, some kind of application, like whenever some kind of batteries or these kind of things are involved. So, application of converters are huge, okay. So, now if you see the operation of the converters, so naturally that is based on the switching property, and whenever switching is there, so first order sliding mode control is quite applicable or quite comfortable to give the performance in presence of the unknown uncertainty or disturbances, okay. So, during the development of theory of sliding mode control for power converter, we are going to talk about very important concept, that is time scale separation property, okay. So, actually if you see the design of power converter system, so basically they have two dynamics. So, one dynamics is fast dynamics and another is called the slow dynamics. And due to fast dynamics and slow dynamics, same like the sliding mode control, if you see carefully, then sliding mode control also basically showing two different kind of property. So, we have two phase, one phase is called the reaching phase and another phase is called the sliding phase, okay. So, reaching phase I have to complete as soon as possible, because system become insensitive with respect to disturbance once sliding phase comes into picture. So, somehow this represent the fast dynamics, and this represent during sliding, that will represent the slow dynamics, okay. So, somehow this is coming from the theory that is called well known as a singular perturbation theory. So, Professor Kokotovic has created or done lot of contribution on this particular domain. So, during the development of sliding mode control, I am also going to utilize the property of the time scale. Now, due to this time scale separation property, it is possible to show that whole control structure is basically the cascaded control structure. It means that you can able to deploy classical control as well as sliding mode control on two different loop, and you can able to achieve the required performance, okay. So, since fast dynamics is associated with the inductor current, and due to that reason we have inner loop. So, in inner loop I am going to deploy the sliding mode control to control the current, okay. And after that, in outer loop one can able to design some kind of PI control such that you can able to achieve the voltage regulation. And direct implementation is possible because sliding mode control is inherently based on the discrete switching or some kind of switching based property, okay. So, and obviously here switching should be very high, and if you have physical circuit which is capable to do that, then you can easily able to get required performance if you employ the sliding mode control. So, this is one of the alternate solution over the pulse width modulation based technique. So, lot of power converters or power electronic circuit is based on this particular design methodology, but if you apply or deploy the sliding mode control at that time, it is possible to show that you can able to get several advantages over the PWM. So, if you see the some classes of the power converter. So it is possible to show that one class of the power converters are actually satisfying the property of bilinear system. What is meaning of bilinear system? If you see this structure, so here control and state both are involved. Okay, so this is linear with respect to u as well as linear with respect to x. If you maintain x equal to constant, then it is linear with respect to u. If you maintain u equal to constant, then it is linear with respect to x. So somehow we are also trying to understand that how to design sliding mode control for bilinear system. Okay, and power converter is going to fall on that particular class. So we have advantage with the power converter because we have just to do two operation, either on or off. So on or off I am going to represent by 0 and 1, and it is possible to show that one can able to design control. Here control design is somehow you are going to control the operation, on off operation. So gain is not going to play any role in this particular design. So topology play a very important role whenever you are going to design the power converter. So power converter, one part is topology, another part is the control design, and both are equally important. Okay, so now we are going to deploy control like this. And what is physical interpretation? When s equal to 0, s greater than equal to 0, at that time this is nothing but the signum x is positive. So if this is positive, then 1 minus 1 equal to 0, so u equal to 0. So you can able to do off operation. If signum s is less than equal to 0, then 1 minus and minus 1, so basically you are getting 1 plus 1. So basically u equal to 1. So in this way I can able to deploy this kind of discontinuous control, then I can able to do or control the switching phenomena. Okay, obviously I can able to design sliding surface like C transpose X, and here C is nothing but the one can easily able to calculate C from this particular expression. So here S I am assuming either positive and negative, and X may be more than 1, and due to that reason if you do this kind of calculation, then you can able to get the value of this matrix C. Now let us try to see how one can able to achieve the sliding mode control. Okay, so in order to achieve the sliding mode control, first I have to design the sliding surface. So sliding surface is proposed like C transpose X. C is nothing but some kind of constant matrix you have to select. Now I will take the derivative. So once you will take the derivative, then x dot comes into picture, and from the bilinear dynamics Ax and u I am going to substitute like this into Bx, then I will get this kind of system. Okay, and what is our goal? Our main goal to make s equal to 0 attractive. Okay, so what is condition of attractivity? It means that ss dot should less than 0. Okay, so somehow you can think like I have this kind of manifold. If s is greater than 0, then s dot should less than 0. If s is less than 0, then s dot should greater than 0. So here what I have done, I am assuming that s greater than 0. So now I am going to calculate s dot. So s greater than 0, then obviously signum function here that takes value equal to 1, and in this way this and this is going to cancel out. So just I have to maintain CTAX, that is less than 0. Now assume that s less than 0. So once s less than 0, then this become positive, and positive and positive, then I have CTBX. So now s dot I have to maintain, since s is less than 0, so s dot should greater than 0, and then this condition comes into picture. Okay, so in this way I can able to maintain or attract all trajectory towards s equal to 0. Once s equal to 0 comes into picture, so in order to maintain trajectory along this particular sliding surface, I required the equivalent control. So using Utkin's method, it is possible to calculate the equivalent control. What you can do? You can put s dot equal to 0. Okay, so if you put s dot equal to 0 and considering at that time signum s equal to 0, so whenever you are applying the Utkin's linearization, at that time we are defining signum s equal to 0, that as a 0, and due to that reason you can see that this equivalent control should lie between 0 to 1. Why 0 to 1? Because we are doing just two operations, 0 and 1. So control whatever equivalent control or whatever average control that comes into picture to maintain trajectory, that will also satisfy exactly same property. Now, if you see the converter, so here I am going to consider very simple structure or simple topology. So I am talking about DC to DC converter. So there are several types of converter. I have buck converter, I have boost converter, buck boost converter, and after that I have Chooke converter. Okay, so in this lecture I am going to talk about buck converter and boost converter. Okay, so what we have seen that whenever we are talking about buck converter, then we are giving some voltage and we have to actually drop down that voltage. Okay, so I have to somehow maintain voltage that is the less than the given voltage Vd. So now we are going to explain that how basically cascaded control structure comes into picture. So here in case of the converter, we have two different rate involved. One is the inductor current and another is the capacitor voltage. Okay, so from here easily you can able to see. So this is a structure of the buck converter, and here I have element like resistor, capacitor, inductor, and this is responsible for switching, and this is some kind of voltage source. Okay, so what is our main goal? If I will provide some kind of voltage here, then I have to drop down that voltage here. Okay, so whatever output voltage that is less than the E, so that converter that kind of converter is called buck converter. And here you can come again. So this converter, you can see that here again I have resistor, I have capacitor, again I have inductor, but switching initially I am employing on the another place. Now we are after inductor, we are placing this switch. Okay, so this converter is called boost converter. Why name boost? Because whatever voltage here you are going to apply, finally whatever voltage you are going to get here, that is greater than this. Okay, so in this way you have buck converter and actually boost converter. Okay, so now I have two things because I have capacitor and inductor. So I have two energy storing element, and due to that Tjan order of system is 2. So state is current as well as state is the voltage. So current is always faster than the output voltage. Okay, and due to that Tjan I can able to deploy the property of singular perturbation, that is actually coined by Kokotovic, and it is possible to show that in inner loop, that is current control loop, I will deploy the sliding mode control, and this is the outer loop. Outer loop I can able to design any PI controller. Okay, so this is sliding mode control loop, innermost loop, and outer loop I can able to deploy any kind of controller, and finally what is our aim? I have to maintain some kind of Vd. So whenever you are going to design, talk about the control design, what is first step? First step you have to do the mathematical model. So mathematical model of the buck converter is not so difficult. What you can do, you can apply the Kirchhoff's current law and Kirchhoff's voltage law. Okay, and I know that I have just two operation, so both operation is denoted by U. So and you can take any value between 0 to 1. So first what I am going to do, I am going to apply the idea of somehow I have this is switch and here I have some inductor. Okay, so what I am going to do, I know that IL current is flowing through this inverter, so I am going to do L DIL by dt. Okay, so IL is the current, so this is nothing but some kind of voltage, and I know that here voltage, whatever voltage that comes into picture, so that is V. Okay, so positive to negative. So finally if you see carefully, then E voltage I am going to apply here. So E voltage, that is nothing but either here E I have written here. Now either E will come into picture or not come into picture, that is depending on the switching sequence, and due to that Tjan I am going to multiply with E. Okay, U into E, so that will cover both cases, and after that now this and minus this voltage, whatever voltage across the capacitor, that is equal to the voltage across the inductor, this inductor. So same equation if I apply here, and after that if I adjust L and IL I am going to place as a x1 and V as a x2, then I will get this equation. Please check it. So by application of Kirchhoff's voltage law, I can able to get this equation. Now you can apply Kirchhoff's current law inside this loop. Okay. So here you can see that IL current is coming, and now this current is going to distribute across the capacitor as well as the resistor. So voltage is V, so current is V by R. So X2 by R comes into picture. Here I have Q equal to CV and dQ by dt equal to CdV by dt, and if you put everything, then you will get this equation. Okay. So in this way you can able to get the mathematical model, second order mathematical model, also just that is justified because I have two energy storage element. Now what is our main goal? I have to maintain voltage Vd that is less than the E. Okay, and I have to justify why that is less than E. Okay, using the help of sliding mode control. So this loop is slower, so I am assuming that x2 dot equal to 0, because first loop, current loop is very fast. Okay, so by putting x2 equal to Vd and x2 dot equal to 0, by applying singular perturbation theory here, x2 equal to 0, and what I am going to do, x2 equal to Vd I am going to put, then x1 you are going to get. So x1 is Vd by R. So from this expression, second equation, you can easily able to get this. Okay. Now what is our aim? By applying sliding mode control, I have to force x1. x1 is nothing but whatever current that is coming from this first differential equation, that is exactly equal to x1 star. So if this phenomena occur, then obviously I will achieve the Vd, required value of x2 equal to Vd. So how to do that? So for this control I am going to apply, because I don't have any choice to apply other form of control. This is bilinear system and this is the attractivity condition, and finally it is possible to show that this kind of condition comes into picture. So in detail I am going to show you. So what is the required condition? I have to maintain SS dot less than equal to 0. So if you want to do that, it is possible to show that x2 is always going to lie between 0 to E. It means that whatever value of Vd, that is going to lie between 0 to E. Okay, and due to that reason, by construction you can able to see that I will get the lesser voltage than whatever we are going to apply, because x2 is nothing but the desired voltage. Okay, so that is going to lie, and this kind of things you can able to maintain SS dot less than equal to 0 throughout the interval. You have to maintain that. Okay, now same kind of things I have written. Naturally this operation comes into picture due to the sliding mode, and S equal to 0, now I have to maintain. So once S equal to 0, at that time x1 equal to x1 star, and what is x1 star? That is Vd by R. Okay. Now once x1 equal to 0, so sliding surface is also equal to 0, and whenever sliding surface is equal to 0, then equivalent control comes into picture. So how to calculate the equivalent control? You can put S dot equal to 0. Okay, so S dot equal to 0 means x1 dot equal to 0 will give you, because S is nothing but x1 minus x1 star, and this is constant. So S dot equal to x1 dot. So if you keep this equal to 0, you will get the equivalent control, and that equivalent control you have to place here. And if you solve it, then you can see that as t tending towards th, then perfectly x2 is tending towards the Vd. Okay, so some kind of exponential convergence that comes into picture. Okay, so in this way one can able to achieve the required voltage. Okay, and in simulation I have taken E equal to 20, Vd equal to 7, and in the simulation you can see that perfectly one can able to achieve this, and other parameters are given like this. Now if you understood the previous operation, so this is also very easy to understand. Now here again I am going to develop the mathematical model of this system, and this is boost converter. And why boost? Because we are going to show you that whatever voltage here on output side, that is greater than the input voltage. Okay, and how basically this equation comes into picture? So if you see carefully, so here whenever u equal to 1, at that time this C and R both are disconnected from the circuit. Okay, but whenever C equal to 1, then actually this is connected with the voltage source. Again I am going to apply the KCL, Kirchhoff's current law, and Kirchhoff's KVL, Kirchhoff's voltage law. So in first equation I am going to apply KVL, Kirchhoff's voltage law. Okay, so here I have L di by dt, x1 is the current, and after that you can see here that once u equal to 1, at that time capacitor is not connected. So that kind of condition is automatically coming from here, but at that time E is here, so E equal to L di by dt. But once this will connected, then what happens? I have this voltage, after that this voltage drop also comes into picture, and due to that reason I have x2 and u equal to 0. So basically minus x2 comes into picture, and L di by dt, that is going to comes into picture by division. Similarly, now what we have to do, I have to apply the Kirchhoff's current law. So once I am on position, then IL current is going to enter here, and that is going to distribute. Okay, so in this way this mathematical model comes into picture. So this mathematical model will represent some kind of system which is called non-minimum phase system. So what is physical interpretation of non-minimum phase system in case of the linear and non-linear system? In case of linear system, if our 0 is on the open right half plane, then that system is called non-minimum phase system. Similarly, in case of non-linear system, if you keep output and their derivative equal to 0, and if the required dynamics is unstable, then that is called non-minimum phase system. So controlling of non-minimum phase system is not so easy. Okay, here control become more difficult than the buck converter, because control is also appear on both loop, means towards the current as well as the voltage. But here again they will satisfy the motion separation principle, means voltage loop is always less faster than the current loop, and due to that reason we are going to apply the again principle of the singular perturbation theory. So I have fast current loop and slow voltage loop. So I have two loop. So inside the loop, inner loop, I am going to deploy the sliding mode control, and outer loop I am going to apply the voltage regulation principle, and in that particular way it is possible to show that our overall performance is robust. Okay, so again what is our aim? So our aim to whatever voltage is here in this side, that should be higher, that so that should be lower than the output side. Okay, so now again what I am going to do, I am going to maintain x2 equal to some value Vd and x2 dot equal to 0. Okay, and based on that I am going to calculate the value of x1. Here you can see that x1 star I have adjusted in such a way such that R is the resistance, but here Vd by E. So one term is the desired voltage by the error. Okay, so I want to maintain this is always greater than equal to 1. Okay, so if this is greater than equal to 1, so it is possible to show that whatever output voltage, that is always more than whatever we are going to give the input. And how to do this job? Using sliding mode control I can able to do. I can define the current loop error like x1 minus x1 star. X1 star is nothing but Vd square by Re, and equivalent control during the sliding I am going to apply this. So how to calculate equivalent control? I have to maintain s dot equal to 0. So I have to maintain x1 dot equal to 0, because this is constant. Vd and R and E all are known to us. Okay, now what I am going to do, once you will see the outer loop by substitution of the equivalent control, then this kind of dynamical equation comes into picture. Okay, so in briefly I have written everything, and after that again I will explain that x1 star is Vd square by Re, x minus x star, and ss dot, it is possible to show now this kind of expression comes into picture. Okay, easily you can able to maintain this kind of condition by seeing the dynamics, and x2 is coming from the solution of this. Again if you see this solution carefully, then x2 will converge to the Vd as t tending towards infinity, because we have some kind of asymptotic convergence exponential, and same kind of things you can able to see here, that now given voltage is 20, but what kind of voltage I want to maintain? I want to maintain 2 times than the applied voltage, and that kind of action one can easily able to achieve by deploying the sliding mode control. Now another main area of the sliding mode control, people has found that if you deploy some kind of dynamic sliding mode control to the system, it means that in place of the actual current here, you can see here what basically we are doing, whatever sliding surface we are defining. So sliding surface is based on the information, exact information of x1 and x1 star. So in place of that, if you design some kind of observer and if you directly feed that kind of information, so for that one extra dynamics is required. So if your order of system is 2, then overall system order become the 4. Okay, and in that particular way one can able to improve the overall performance of the control loop. Okay, so this kind of feedback is called dynamic output feedback, and dynamically we are going to actually apply I star here, and if you see carefully, then I have observer system, that is extra system, that comes into picture by the copying this particular system, and I am going to give some kind of initialization. Again problem, Vd I am going to maintain required value, and then based on that I have to maintain I star current loop. Okay, so for there I am going to deploy some kind of sliding mode concept based on some kind of observer. Okay, and obviously we are going to utilize here simple observer, Leuenberger observer. Okay, so now obviously observer dynamics is exactly similar like the plant dynamics, and stability analysis, asymptotic stability is enough. Here you can able to deploy other observer also, sliding mode observer also you can able to deploy, and sliding mode control is designed based on the observed current rather than the measured current. Okay, so during doing this it is possible to show that overall actually performance of control system is going to increase. Now what is the role of sliding mode control? So they are going to actually observe the current track with the reference current, and after that using the concept of the equivalent control, it is possible to show that one can able to maintain real current as well as the real voltage, and during this particular process reduced order dynamics comes into picture. It is possible to show that original system order is 2, whenever you are going to design the observer, so again order is 2, so total order is 4, and during sliding one order is raised, so overall order is 3. Okay, so in that particular way reduced order dynamics comes into picture. We are going to see this through the mathematical equation, and observe output voltage converges to the desired voltage that we are going to set. Okay, and obviously existence of the sliding mode control comes into picture by selecting the proper initial condition. If you are not going to select this proper initial condition, then some kind of energy mismatch comes into picture, and that will deteriorate the overall control loop. Okay, so first I am going to do or develop some kind of observer based control for the buck converter, and after that again I will going to move for the boost converter. Okay, so this is the actually structure of the current loop of the buck converter. What I have done, I have added the correction term and I have copied the dynamics, and due to that reason I have used here x1 cap. So we if you remember the design of observer, Leuenberger observer, so what is first step? Whatever known you can copy it inside your computer. Okay, and after that you can just add the correction term. So here only one correction term we are going to add, second dynamics we are going to copy as it is, because somehow sliding mode is going to deploy with respect to first dynamics. Okay, but we have to show that x1 cap and x2 cap both will converge asymptotically to the original value x1 and x2. So how to prove that? So for that I have to actually analyze the error dynamics. So error dynamics I have calculated between x1 is the original current and x1 cap is the estimated current. Similarly, x2 is the original voltage and x2 is the estimated voltage, and we are going to take the derivative of this, and now it is possible to show that overall dynamics is second order dynamics. Okay, using Laplace transform also you can able to see this polynomial, and this polynomial is always positive, and due to that reason it is, or Hurwitz also, and due to that reason it is possible to show that x1 and x2 both tending towards the x1 bar and x2 bar both tending towards 0 asymptotically. So once x1 bar tending towards asymptotically, then it is possible to show that x1 is tending towards x1 cap. Estimated current is actually exactly equal to the real current, and similarly estimated voltage is equal to the original voltage, vice versa you can easily able to write. Now sliding surface, you can see that I am going to design based on the estimated current. Okay, so here control is also based on the estimated sliding surface. Okay, and now sliding mode is going to occur with respect to estimated surface, that is given like this, and due to that reason x1 cap is going to converge to Vd by R. Okay, and at that time I have to calculate the equivalent control. So how to calculate equivalent control? So from here easily you can see that x cap is x1 cap, this is 0. So basically x1 cap equal to 0 if you substitute in the observer dynamics, then you can able to get the equivalent value of the control. One more important point here I am going to highlight, that whenever you are deploying the observer, at that time whatever control you are going to apply to the plant, same control input you have to deploy to the observer which is running inside your computer. Okay, now after calculating the equivalent control, what I am going to do, since I know that during sliding S1 cap equal to 0 and average value of S1 dot also equal to 0. Okay, and due to that reason this dynamics, first dynamics, that is going to collapse. So how many dynamics now I have? This is coming from the plant, x1 dot and x2 dot, and x1 S cap equal to 0 and x1 cap dot also equal to 0. It means that these first dynamics will collapse, and due to that reason I have just second dynamics, but at that time equivalent control comes into picture. So you have to substitute the control by equivalent control. Okay, and after that again I will define the error like this, and now this is the error dynamics, and it is not difficult to show that x1 is going to converge to x1 cap by doing the analysis of this differential equation. x1 bar star equal to 0. Okay, so by designing L is the nothing but the gain of the inductor, and that is always positive, R and C are positive. So it is possible to show that this phenomena occur, and due to that reason x2 cap is actually going to converge to Vd, and in this way voltage is going to match to true voltage. And how to talk about existence? You have to maintain this x cap and x cap dot that is less than equal to 0. So if SS x cap dot less than equal to 0, then this kind of condition comes into picture. Please check it. And equivalent control, how to calculate the equivalent control? So you can just keep this equal to 0, then you will get this kind of equivalent control. One important point, if you calculate the store energy, so once convergence occur, the store energy, mismatch of the stored energy, because x1 is going to converge to Vd by R and Vd is going to converge to x2, so that is actually become 0. Okay, so in this way you can able to check that your control is working fine. Okay, so once sliding mode occur in finite time, at that time x1 is going to converge to x1 hat, that is Vd by R, that is set by us, and after that x2 is converged to Vd. Okay, and energy is tending towards 0, and this is the simulation. So in simulation what I have done, initial condition I have told you that whenever you are designing observer, then initialization of this particular system is very important. Okay, so proper initialization is required. If you will do 0 initialization, at that time some more difficulty comes into picture. Okay, so more energy is injected inside the system. Okay, and due to that reason means I have not taken x1 cap and x2 cap equal to 0, some finite value I have taken. Okay, and it is possible to show that using this again I can able to achieve the buck operation. Okay, similarly you can able to extend this concept for the boost converter. Okay, again what I have done here, this is the dynamics of the boost converter, and I have added some kind of correction term. So during copying I have keep x1 cap here and x2 cap here, and similar kind of copy I have done for the x2 cap. I have just added correction term here because I know that in innermost loop I am going to deploy the sliding mode control. Again what I am going to do, I am going to define the error, and in error coordinate I will get this kind of equation. And using Lyapunov analysis, since this is highly nonlinear system, because here I have u and u is depending on the s, and due to that reason I have taken the help of Lyapunov function, and it is possible to show that x1 cap, x1 bar and x2 bar both equal to 0. So x1 bar and x2 bar both equal to 0, and x1 bar if you define by x1 minus x1 cap or x1 vice versa you can define. Okay, based on that dynamics is going to change here, negative and positive is just going to change. Okay, so any way you can able to define. Now what we are going to do, I am going to take this as a sliding surface. So now in sliding surface I am going to take the estimated value of the current. Okay, here since whenever we are seeing the dynamics of the boost converter, so control is explicitly appear with respect to current as well as voltage, and at that time 1 minus u comes into picture. So if you can define like this, then complementary thing that V comes like this. Okay, where V is nothing but 1 minus u. Okay, so once sliding mode occur, at that time by the definition of this x1 cap equal to 0, so x1 is tending towards Vd square by Re, and V equivalent, how to calculate the equivalent control, S you can take and their derivative equal to 0, so x1 cap equal to 0. And what is x1 cap? This is the dynamics of the observer, so you can just put x1 cap equal to 0 and equivalent control you can calculate, that is given like this. Now I have current, that is actually this is the current dynamics, this is the voltage dynamics, and one dynamics is going to collapse because during sliding I have to apply equivalent control. So due to equivalent control, average value of x1 cap dot that also equal to 0, and due to that reason if I substitute equivalent control inside the system, then order of the system, that is 2 for the original system plus 2 that is running inside the computer, and now due to sliding 1 is collapse, and due to that reason minus 1 occur, and total order is 3. So all 3 order you can able to see from here. Okay, now I have to show the stability. So how to show stability? Again I will define the error dynamics. Okay, so this is the current error, this is nothing but the voltage error, and again this is highly nonlinear system. So how to prove that x1 and bar equal to 0 and x2 bar equal to 0 at least asymptotically, how to prove? So for that one can able to take the help of the Lyapunov function. Okay, so before doing that, what we are going to do? We are going to do this kind of substitution. In place of x2 we are going to put x2 cap minus x2 bar, because I have defined here x2 bar equal to x2 cap minus x2. Okay, so these are the simplified dynamics, please do by yourself, and after that we can define the Lyapunov function, and V dot is less than 0. So V is greater than 0 and V dot is less than 0. Okay, so in that particular way it is possible to show that x1 bar star and x2 bar both are tending towards 0, and as this is tending towards 0, so x1 is going to tending toward x1 cap, and that is nothing but the x1 cap desired kind of current that comes into picture. Once desired kind of current comes into picture, so desired voltage comes into picture, and you can also able to see if you deploy this kind of transformation, then this is nothing but some kind of linear system. Okay, and in linear system this is already 0, so there is no other choice. Y is basically Vd equal to x1 square, that kind of things comes into picture, and in this way I can able to prove that as t tending towards the infinity, x2 bar is actually tending towards the Vd. So that kind of things comes into picture. Here definition should be x2 bar minus Vd, then only y tending towards 0, then this kind of condition basically comes into picture. Okay, and in this way I can able to achieve the desired objective. Necessary condition, because you have to maintain SS dot less than equal to 0. Here sliding surface I am making based on the estimated current, and due to that reason x cap comes into picture, and after that I have to substitute S dot equal to 0, then I will get equivalent control. But equivalent control should lie between 0 to 1. Why? Because in whole converter operation either I am doing the 0 and 1. Okay, so somehow we are controlling the duty cycle. Okay, now energy matrix if you will see, so once convergence occur, so energy is equal to 0. And again in simulation gain I have taken very high, and it is possible to show that again one can able to maintain the voltage, and by the use of the dynamic output feedback or dynamic sliding mode control, because and output is here current. Okay, so now I have already told you that if you initialize like 0 0, then obviously you have to wait for large time such that these two mismatch is actually energy mismatch is minimized, and due to that reason proper initialization is always required. So what is key contribution? We have talked about sliding mode control of power converter, and power converter is actually nowadays due to EV, boom of EV, that is very essential. Okay, so now you can able to extend this kind of concept for AC to DC, DC to AC, buck boost or Chuk converter, any kind of converter you can able to extend this concept. We have discussed both the observer based, and after that voltage regulation and stability based only upon whenever that is required we have actually used that, and theoretical and implementation, MATLAB implementation I have also shown. And obviously sliding mode control is very natural and robust performance, and actually one can able to also check the stability and energy based performance matrix also one can able to evaluate if you are going to deploy some kind of sliding mode control loop as a current control loop. Okay, now before the ending this particular course, so this is last lecture of this course, sliding mode control and application. So this is the picture of my supervisor, Professor Vigyan Bandyopadhyay. So now he is retired from IIT Bombay, and he is a visiting professor at IIT Jodhpur, and I was doing PhD at that time. This is the picture around I think that 2012 or 13, and this is Asif Chalanga. Several times we have developed a lot of theory with this, and this is Abhishek. So Abhishek is now professor in IIT IIT Roorkee, and after that this is Prasidh, we are telling Prasidh Bhaiya. So he is again, so almost all are professors. Okay, and he is working in industry, he is master student. And in 2012 my supervisor sent me to Professor Utkin, and Professor Utkin is actually arranged some kind of his school to teach sliding mode control to young student. Okay, and I am feel very lucky because I have learned lot of concepts. Okay, particularly application point of view, theoretical point of view, how flip-flop solution and Utkin's regularization are different. So in 6 days, every 6 days he was taking lecture of 6 hours. So within 36 hours he taught me the classical sliding mode control and some part of the higher order sliding mode control. I will again feel lucky. You can see this guy, very big guy. So this is Professor Leonid Friedman. Okay, and this is the group. Here he is the Professor Morino. So lot of Lyapunov proof you have seen that in this lecture I have used. This is also one of the professor in same Mexico University, and these two are my friend. Okay, so during my stay, this is actually Hector, and this is Tonio. So both has actually nice discussion with them, nice dinner and every time. So 2 months I was there, and during this visit I have learned a lot how basically sliding mode control develop, what kind of lacuna inside sliding mode control. So every story I can actually heard from this professor, and he is always very motivated and always sharing lot of things. Okay. So in any VSS or variable structure control, you can able to see this big guy. Now here this is the Professor Levant. Okay, so Professor Levant visited India in 2012, and he is Professor Jingyu, those who are working in terminal sliding mode control. So I have actually collaborated a lot. Still we are collaborated with the Professor Jingyu. He is now in Australia, and he is my supervisor. So supervisor is actually arrange this conference VSS. Levant is very serious guy, so he is very less talkative. Okay, it is very difficult to collaborate with him, but concept wise he is very sound. And here this is basically the Ferrara. So lot of work is actually done by Professor Ferrara, and recently in 2024 my supervisor has organized one school, IFAC sponsored school, that is held in IIT Jodhpur. So this is Professor Phulwani. So non-linear surface kind of work that is done by Professor Phulwani. Again, he is my friend Abhishek. I have already told you that Professor Abhishek is professor in IIT Roorkee, and he is in IIT Jodhpur. And this is Sarah Spurgeon. So very famous sliding mode, classical sliding mode book you can able to see. This is Saleja ma'am. So this is just my sister, So during my PhD she has helped me to done a lot of experiment, and during several presentation I have shared the experiment, that is actually contribution of this particular lady. Okay, so with this particular remark I am going to end this lecture. Obviously I am going to connect you virtually, and at that time I will share more story, more unsolved problem I am going to share. Okay, so I have taken almost 61 lecture, and most of lecture is somehow between 30 to 35 minutes. Okay, so please go through each and every lecture. Some lecture may be very fast. Okay, but what you can do, you can pause and go through it. Okay, and whenever you have confusion, then do not forget to contact me. You can just send me an email. Okay, so my email ID is syamkamal.triplee@iitbhu.ac.in. So I think that within 1 to 2 days I will reply. Okay, for that email. So with this remark I am going to end this lecture. Thank you very much.